Hi there, this is Ian McTavish. I'm the founding mentor for Team 4152, Hoya Robotics, located in Huntsville, Ontario. And this is part 1 and 2 of designing a gearbox. So this tutorial is geared for Team 4152 new members, but hopefully anybody in the FIRST Robotics community can find use of it. This is going to be a series of tutorials. The goal for this one is to design a gearbox, and then later on we'll be designing tutorials on how to manufacture the gearbox so that all the different concepts for making complex robotic parts can be covered. First off, a quick thank you to all of our sponsors. These are our Team 2019 sponsors, and in January we'll be updating this with our 2020 sponsors. I have to give credit where credit is due. Team 610, Ryan Tam, has created this phenomenal resource, and the link to the PowerPoint is right there. It's a PDF document, and it has got all kinds of design tips, and this tutorial is based on one of the tutorials he has in there. The other key thing is that we are using Onshape, and you're going to get a lot more out of this tutorial if you've learned the basics of parametric design in CAD. And Onshape for FIRST Robotics has an education account that you can create, and there's a series of tutorials, and I highly recommend you work through all of those tutorials so that you're up to speed on these skills. Basically, you can create two-dimensional drawings, make those drawings into three-dimensional parts, and then assemble those three-dimensional parts into complex machinery. Step 1, firstinspires.org. This is the website for FIRST Robotics, and I'm just going to quickly head to that website. Under the programs menu, they have FIRST Robotics competition, and there's a couple places to check. Number 1, they have a blog, and in the blog they do have usually a blog post where they announce what kind of motors you can use for the upcoming year. And you can also go into the game and season information, and in there's all kinds of mechanical resources, and that kind of information is just crucial to be able to get your performance data for your different robots and for your motors and things like that. So this is an example of the 2017 motors that we had. Most of these motors we still use. For the 2020 season, there's a couple new ones that are really worth checking out. But you can see in here you have all the information, what maximum power it has, what stall torque. So stall torque is basically how many ounces per inch of force before the motor will just stop turning the shaft. The free speed, so this is if there's no load on the motor, how fast it will go. The free current, so obviously using up too much amperage could be an issue, so you can calculate that. What is the current when it's going to stall out? So something on a 40 amp circuit like a sim motor is not likely to stall out because the 40 amp fuse will probably flip before it stalls. And then how much weight is the motor? Just a quick rule of thumb, if you are using motors in FIRST Robotics, for Team 4152, our go-tos are Sims, Mini Sims, and Neos, and those are great if we need a fairly powerful thing like an elevator that's going to lift a lot of weight or a drivetrain. And if you need speed, things like Redline motors or 775 Pro, really fast, great for shooters and things like that. We want to experiment with some of the new motors like the Falcon. Cost is our biggest issue, so we need to look at what motors we have. There's other motors like bag motors that we use for certain specific requirements. Now, this is a really key thing, is that when you're designing a gearbox, you need to plan ahead. And there's a bunch of tools out there. One that we often use is the JVN design calculator. So this is the JVN design calculator. It's a spreadsheet. There's a lot of different tabs. Highly encourage you to read it, but basically you pick the tab based on what you're trying to do. So if you had a linear mechanism like an elevator or something, you could fill it in. Anything blue is a drop down, so you can pick what type of motor. These white ones will automatically change based on the type of motor. The pink ones you can modify, so we decided 2 motors per gearbox. Always kind of assume that the motor is not going to be running at 100% efficiency. If you have a linear mechanism, how far is it traveling? How heavy is the item that you're pulling? If there's a pulley, what's the pulley diameter? And then these are your gear ratios. So these are the values that you play around with and enter in, and it will calculate what speed it's going to take to move that distance, and it will also calculate what the current draw is going to be. Now, the biggest thing is that we're on a 40 amp circuit, so we want it to be under 40. This is getting pretty close to 40, so for this particular application, we might decide to add a third motor to spread it out a little bit more, or change the gearing to a more aggressive gearing, but the compromise is it'll be slower. So it's all about what compromise you're going to have. The other thing is that you need to pick your gears. So we use Vex for a lot of our gears, and basically you need a pinion. So a pinion gear is something that will attach to the motor. So you can see here, Sims are the same pinions as mini Sims, so we can look through these and the number of teeth, what the material's made out of, what the DP, so the diametrical pitch. So those are all some of the key things that you need to use. The other thing is down in here, you have your drawings and everything. So this is really key, because as you're picking information, you want to look through it and you want to decide, okay, if I'm going for this, I need to know what the pitch diameter is. So 0.6 for this one, because that's going to be used in your diagram. So you need to be able to find the drawing for the specific tooth or pinion that you're going to be using, so that you know that. And same thing, so these are the driven gears. So with the driven gears, we typically use 1/2 inch hex bore, so that's why we go to that particular section, and we can see the different teeth. And same thing, they have drawings that we can take advantage of. So those are all part of the handy aspects. And we decided in this particular thing that we were going to use a 12-tooth pinion driving a 60-tooth gear. That was not, the amperage for that was far too high, so we added a second stage where an 18-tooth pinion would drive a 60-tooth. So that gives us this ratio, and it works for our current draw. So this is just a tutorial. Obviously we would modify this if we wanted to have a quicker speed, or if we wanted to reduce the current draw so that we're not encountering brownouts. As I mentioned on the drawing, you want to make sure you know the pitch diameter, and in Vex all of the dimensions are in inches, so you need to know that. And same thing, this is the 18-tooth gear. It's got a pitch diameter of 0.9, and our 60-tooth has got a pitch diameter of 3. So those are the gears that we're going to be doing in the tutorial, and in our next video we are going to be going over using Onshape to plan and work on our gearbox. Thank you for listening, and I'll be posting the additional tutorials on this website later on.